Hey guys, my name is Will Buchanan, and this is my lab 4 covering circuits. So a quick intro, the main purpose of this lab is to gain a general better understanding of circuits and to understand how things like capacitors and resistors can impact our circuits. And here are some important concepts listed that we'll get into later, and we're going to improve our understanding of those while predicting the voltages and certain times taken given parameters. And some important principles include Ohm's law, the node rule seen here, the loop rule, which is basically conservation of energy in circuits, and time dependence in resistor capacitor circuits. Here we see Ohm's law, and here we see resistor and capacitor formulas, and we see the difference of series versus parallel. So a quick overview, part 1 is charge conservation and energy conservation in series, and part 2 is resistor capacitor circuits, and part 3 is time-dependent voltage across a discharging capacitor. And setup and assumptions, we're using an online ideal model. So the resistance of wires and ammeters, instead of being really low, will just be 0. And the system's perfectly isolated because we can have an ideal model because it is online. And part 1, series circuit. So here, when looking at this setup, we can add up the total resistance and add up the voltages of the 1.5 volt batteries. And using Ohm's law and nodes rule, we get an expected current of 0.0204 amps. And our predictions were proved correct by this model seen here. And when we replace one of the ammeters, so we replace this top ammeter with a voltmeter, the voltmeter reads 3 volts and the ammeter reads 0 amps. And this is because the voltmeter does not close the circuit. So these total 3 volts are just shooting up to the voltmeter, getting recorded, but not continuing through. And that is why this reads 0. And now we are looking at the voltmeter readings from this point to this point and this point to this point and so on. So we see that over a battery, it'll be 1.5, which makes sense. But then when we go across this first 47 ohm resistor, we get a reading of 0.96 volts. And then when we go down to the 100 ohm resistor, we get a reading of 2.04 volts. And this is just showing that an ammeter and wires have no resistance. So here we can take the 3 volts from the batteries and subtracting the voltage charge from the 47 ohm ammeter and the 2.04 voltage charge from the 100 ohm voltmeter. Those luckily add up to 3 and help prove our loop rule. So we can be confident in those readings because everything goes to 0 volts when added up. And here we are asked to complete the graph of the potential voltage across the entire circuit. And we see here this first resistor causing a drop in potential voltage. And then here we see the second resistor, the larger one, causing a much bigger drop, which almost twice as big, which makes sense. And we see that drop right here back to 0. And whoopsies. And here we see that the 47 ohm resistor is actually resisting 48 ohms, and the 100 ohm resistor is actually resisting 102 ohms, which is pretty close and probably just a discrepancy caused by the computer program not being the most precise. And voltmeter and ammeter in parallel, the question is, when an ammeter and voltmeter are placed in parallel, why does the ammeter still have the same reading? And that's because the voltmeter has such a high resistance that the majority of the current will just still go through the ammeter. And here we have a 10 ohm light bulb and a capacitor, and the capacitor here takes 8 seconds to charge up and about 8 seconds to discharge. However, when we change this light bulb to 20 ohms, it takes roughly twice as long. So we see the connection between capacitor charge and discharge time and the resistance present. So here we're looking at time-dependent voltage across a discharging capacitor. So on the second half, when it's releasing that charge back into the circuit. And obviously it starts at 9 because we have one 9-volt battery. And then as it discharges, it goes all the way to 0. And then taking the natural log of the change in voltage divided by the original voltage, we take these values and we plot them, and we can use the slope to find the resistor capacitor time, which is 5.62 seconds. And the theoretical calculation of the resistance times the ferrons is 6 seconds, which is very close. So we can be confident that both methods worked. And some sources of error. The main source of error that I have is that when I had to click for each second rather than being able to like press a step button. So I wasn't always getting exactly 1 second steps. So that'd be my only potential source of error, the main one I could find. And sources of error were low due to using a computer model. And what if you used an actual ammeter? The actual ammeter has a tiny bit of resistance, so the currents throughout the lab would have been a little bit lower, but still pretty similar. And then if we were doing this lab in real life and used a real battery to charge a real capacitor, it would basically charge up almost immediately. And the only thing that would stop that would be resistance in the wires. And the ideal model would predict that the capacitor charges to full immediately because wires do not have resistance in the ideal model. And here's our conclusion, basically noting loop rule work. Currents and voltages can be calculated using Ohm's law, without capacitors at least. And we learned a little bit about capacitor charges and how they're time dependent, maybe based off resistance, and how they can charge and discharge. That's all I have. Thank you for watching.